9, Rosen, section 9.6 on partially ordered sets, a type of relation or a property of relation that has, a relation that has the properties reflexivity, antisymmetry, and transitivity, we say is a partially ordered set. One useful way to analyze partially ordered sets is with what we call a Hasse diagram, and it is based upon the digraph of the relation. Remember, we can express a relation using a directed graph, but we're going to leave out certain edges due to reflexive and transitive properties. Here's an example of the partially ordered set where we have 1, 2, 3, and 4, and the relation is less than or equal to. So there's the digraph for that, and if we remove all of the loops, then we will have a slightly more visually appealing representation, but we also want to remove the edges due to transitivity, and here we have in C a Hasse diagram. And one thing that hasn't been mentioned, which I'll mention on a later slide, is that ordered pairs where the second element of the ordered pair is always higher than the first element of the ordered pair. And when we do that, we don't need to add the arrows. So again, we delete the loops, we delete the edges due to the transitive property, and the Hasse diagram is depicted in C. We drop the arrows, and we ensure that the second element in any ordered pair in the relation is higher than the first element. All right, so this tells you to write a digraph for the relation. I'm going to suggest you don't do that, but we'll just go with the slide as it's written because it does have that issue of arranging vertically the elements properly. And then again, we remove loops, or we just never draw them in the first place. We remove transitive edges, x, y, such that there's a x earlier than z and z earlier than y. We just leave off the edge x, y. And then here is what I was getting at. We arrange each edge so that its initial vertex is below the terminal vertex. And then we remove all the arrows because we know that all of the lines point upwards. All right, so here's an example from our textbook. We're constructing a Hasse diagram of the set containing 1, 2, 3, 4, 6, and 8, and it's the divides relation. And here's the digraph, or the directed graph for that relation. You can see it's kind of messy with lots of loops and arrows going from one to every other element because one divides everything. So we'll remove the loops, and then we'll remove all arrows such that have to be there due to transitivity. So we would remove that arrow, and then we would remove this arrow. And we don't need 3 and 12 because 3 goes to 6 and 6 goes to 12. So we'd remove those to get something that looks like this. So here's the Hasse diagram for that partially ordered set. But I'm going to slide it over, and I think we can just draw these directly from the sets themselves. If I look at my set, I know that the lowest element is going to be a 1 because 1 divides everything. Write that down. Where does the 2 go? 2 is going to go above 1 because 1 divides 2. And where does 3 go? Well, 3 is going to go at the same level as 2 because 2 doesn't divide 3, but 1 does divide 3. Where does 4 go? Well, 4 will go above 2 because 2 divides 4. And 6 will go above 3 because 3 divides 6, but also 2 divides 6. And that isn't caused by a transitivity relation, it's just another ordered pair in the relation. And then 8 will go above 4 because 4 divides 8. And 12, it'll be at the same level as 8 because neither 12 nor 8 divide each other, but 6 divides 12 and 4 divides 12. So I think it's okay to just try to write down the partially ordered set, Hasse diagram, directly from the partially ordered set. Okay, let's talk about a couple of concepts. Oh, here's another Hasse diagram. This is on the power set of A, B, and C. So there'll be 8 subsets, 8 vertices, 2 to the 3, with the subset relation. And I'll just put it up here. The empty set is going to be the lowest because it is a subset of every other set. But it's a subset of each of the single element subsets, which themselves are subsets of the 2 element subsets. So we don't need a line from the empty set to that, to the 2 element subsets. And then all the 2 element subsets are subset of the 3 element subset. You can kind of see that these are all about at the same level. They aren't comparable, but they're comparable to those above, some of those above and below. All right. A couple of definitions, maximal and minimal elements. We say that an element of a poset is maximal if it is not less than any element of the poset. In other words, there's no B such that A is less than B. And similarly, an element is called minimal if it's not greater than any element of the poset. Also, A is the greatest element if it is the only maximal element. And A is the least element if it is the only minimal element. Let's look at an example. Here is a Hasse diagram for the divides relation on these integers. And what are my maximal elements? Well, I have 3 of them because 12 does not divide anything else on that in these elements. 20 doesn't divide anything else in these in any of these other elements, and 25 does not divide anything else in these elements. But there is no maximum element because I've got 3 maximal elements. How about minimal elements? Well, nothing divides 2, so that is a minimal element. And nothing divides 5 of these elements, so that is a minimal element. But I don't have a minimum element because I have 2 minimal elements. And that is Hasse diagrams and using them to find maximal, minimal, maximum, and minimum elements.